Go.
Yeah, you can't do
All right. You're right. I've got two magnetic pucks, and between these two magnetic pucks, what we're saying is that there's a uniform magnetic field. Magnificent magnetic field. It's fabulous. And they're all the magnetic field is oriented the same way. That's what we mean. It's uniform in orientation. It's also the same strength, so it's uniform in intensity. It's completely uniform. Okay? And the red arrows are indicating the direction of the magnetic field. Now what I want to suggest is that we introduce a proton, a wandering proton if you like, into the magnetic field. And I'm going to put the proton in the foreground. I'm going to actually put it at the same point that I've drawn this magnetic field. So it's going to be in the foreground in the magnetic field, a proton. Okay, so a positive charge. I'm not going to make the mistake that I made earlier of introducing a negative charge into a magnetic field, because then we got into arguments about left-hand rules and things like that. It's not your fault, it's my fault. I misspoke. So we have a proton in the foreground, and I'm going to give it an initial velocity to the right. Pardon me? Well, let's see. Let's get the right hand out. Get your right hand out. You've got it drawn. I want you to make your fingers go in the direction of the magnetic field. So in this case, I'm going to have to convolute myself around. Fingers going in the direction of the magnetic field. You can do it up to the screen if you want. Your thumb going in the direction of the moving charge's velocity. What direction is that? Right. To the right. What direction is this charge going to get pushed?
Backwards.
Getting pushed into the page. Okay, so this is kind of a hard thing to draw. So let's try and draw it in 3 dimensions. I'm going to do it as a green arrow. And it's going to go into the page. Okay, I know it's hard to see the 3-dimensionality, but this is an arrow that's pushing into the page. That little tiny green arrow on the left-hand side of my proton, little tiny green arrow pushing into the page. Okay. Okay. Now that means that this thing's getting pushed into the page, or to the, you could say the center of the pucks. Can you guess where I'm going here? As this thing tries to go tangential to this circular puck, it's going to get pushed towards the center. Let's see what happens if it was going at this point.
That's proton 1.
Let's see what would happen if it was at this point here, and it's going away from us. So I'll just do an up arrow, but we'll know in our hearts and in our minds that that means that it's away from us. Okay? Let's get our right hand ready. You've got the magnetic field going down. You've got now the proton going into the page, away from us. What direction is it going to get forced? Again, to the center of the circle. Yeah? Okay, so we've got this thing that does this thing. Yeah? What if I go into the background and I take the same charge? And at this point, it's traveling to the left. Magnetic field hasn't changed. It's a uniform magnetic field. Fingers ready. Magnetic field down. Positive charge going to the left. It's getting pushed towards us, right? So now I'm going to draw it with my green arrow coming towards us. Okay. Yeah, everybody's just going to be moving their grasping at the air like you got something wrong with you. All right. Now what happens? You tell me. Yeah, every time. If it's traveling towards you out of the page, then we can talk about this charge coming towards us out of the page. Magnetic field again oriented downwards, but this time the charge is coming to us out of the page. Again, it's going to get forced towards the center. Okay? Okay, and thinking through that idea in 3 dimensions and really getting your hands into it, you can go and play with the applets. I'll give you the links. But think through it. Thinking in 3D can be tricky sometimes. And reaching your hand around it can be tricky. And if you go into a higher level electromag class and you see all the loonies with their hands out, grasping the page and doing all kinds of right-hand rules, you'll know what they're doing, okay? This is hard stuff to maybe think through. Anyways, in each case, the formula QVB sine theta is at play. And we're talking about the force that's applied because the velocity of that charge in the presence of that magnetic field. And in this case, I've been very careful to make sure that the magnetic field and the velocity of the charge are always at right angles to each other. Okay? I was pretty careful about that. I introduced a horizontally launched proton between these magnetic plates. Pardon me?
But if it was like going on an angle, it would change.
Yeah, it would do a corkscrew, wouldn't it? Because it would have a y component to its initial velocity. Yeah, Tyler brings up a good point. I only talked about having a proton introduced that had x component to its velocity. If it had a y component to its velocity, it wouldn't just go in a circle. It would go in a corkscrew. And that would be pretty neat because, hey, I know that it's sometimes a bit silly to introduce like gases and things like that to scenarios, but what if we did this sort of thing in maybe a fluorescing gas scenario? What if I did all of this inside of a fluorescing gas?
You see it.
Would you see like a blue glowing trail or
That
something?
would be really cool if you could do that.
Yeah.
Can we do it on demo day?
We can't do that one on demo day. I don't have the equipment. But what if, yeah, maybe we can find a demo of it. What if you took the same charge and you fired it into a fluorescent gas between two magnetic poles and you fired it with a Y component? Yeah. You'd corkscrew down until you hit a magnetic pole, I suppose. That would be pretty neat, and you get this kind of glowing trail. Okay?
And you would
Make
so
glowing
if it was going
tornadoes.
horizontally, it would just be